2 of Module 12 in the book Problem-Solving Guide for Mechanics and Thermodynamics. The subject of this lecture is thermodynamics. Of course, if you just sit there and wait for the knowledge and skill to seep into your brain, it's not going to work. You have to be an active learner, think about what's going on, pause the video frequently, have a piece of paper and pencil handy, and try to understand. Here's a sample problem involving thermodynamics. You should know how to do this for the exam. 10 moles of an ideal monatomic gas are in a container with the volume of 10 liters. The temperature is 300 kelvins. The gas is heated to 400 kelvins at constant volume and then heated to 500 kelvins at constant pressure. You should be able to draw that on that diagram. Draw those two transitions on the diagram. Then calculate the change in internal energy of the gas, the thermal energy transferred to produce this change, and the total work done by the gas during the process. So the previous lecture talked about internal energy, work, thermal energy transferred. We can use measurable quantities such as pressure, volume, and temperature to calculate them. We know the relationship between the internal energy of a monatomic ideal gas and temperature. It's 3/2 nRT. We know the relationship between PV and T, as well as the number of moles of the gas. And if it's a constant pressure transition, we can calculate the work done with P delta V. So now we need to develop the skill in handling all of these equations. It's always a good idea to draw a diagram so you can see what's going on. And if you're doing problems in thermodynamics, a pressure versus volume plot is very useful. So here's pressure versus volume, and it has a transition on it. We can read off the pressure and the volume, and let's assign a number of moles. So we have 5 moles of an ideal monatomic gas. Starts off at 3 million newtons per square meter, about 30 atmospheres. And then the volume increases, but the pressure stays the same. How does it do that? Volume's going up, but the pressure stays the same. Ooh, I know how you can do that. You got to heat it up. You got to heat it up. So you're dumping Q into this thing to get it to do that. Then, when it gets to 10 liters, then you take your thumb screw and you tighten down the piston so it can't move. The volume's the same. The volume's 10 liters the whole time. And the pressure drops. How do you get the pressure drop without changing the volume? Well, you cool it off. So you dunk this thing in some dry ice or liquid nitrogen or something, and we actually can calculate the temperature at the 3 relevant points. PV is equal to nRT. We have P, we have V, we have N. We can calculate temperature. Right here, it's 361 kelvins, and it better be hotter over here. 722 kelvins. And it better be colder down here. And it is. 241 kelvins. Okay, I think we're ready to go. 10 moles of an ideal monatomic gas are at a pressure of 1.04 times 10 to the 6 newtons per square meter in a volume of 40 liters. That's the initial state. Then it's cooled at constant volume until the pressure is 779,000 newtons per square meter. That's state 2. Finally, it's cooled at constant pressure until the volume is 32 liters. That's state 3. Fill in the table. Here's Q, delta E internal, and W. So from state 1 to state 2, what happened? From state 2 to state 3, what happened? From state 1 to state 3, that's the whole thing. We're just going to add up these two columns to get that. Well, PV diagram. What's going on? So there it is. Starts off at 40 liters. That's right here. 1.04 times 10 to the 6th. That's right here. Cooled at constant volume. There it goes straight down until it's 779. Right here. Then it's cooled at constant pressure. The pressure doesn't change until it gets to 32. That's right here. What now? Well, the internal energy is just 3/2 nRT. So if we calculate the temperatures, which we can, we have the number of moles, it's 10. We have the pressure, we have the volume, we can get the temperature. Let's do that. The ideal gas law, PV is equal to nRT. For state 1, we calculate T. There's the pressure. We have to convert to meters cubed because of the gas constant. Joule is in Newton meter. Pascal is in Newton per square meter. So there's 40 liters in units of meters cubed. And we can calculate the absolute temperature, and we get 500.4 kelvins. For state 2, it's 374.8. We cool it at constant volume, and we cool it at constant pressure. It should be colder. 299.8. Okay. Now we can calculate the internal energy of the gas, and thus the change in internal energy of the gas. So here's the internal energy of state 1, 62,400. State 2, the temperature is different, everything else is the same. State 3, temperature is different. So change in internal energy gas is easy, we just subtract them. So from 1 to 2, it dropped 15,600. From state 2 to 3, it dropped 9,350. And from 1 to 3, about 25,000. 25,010 if you want 4 significant digits. So now we can think about the W and the Q that produced this change. From step 1 to step 2, there's no change in volume. Cooling at constant volume. It was 40 liters the whole time. The piston does not move. How can the gas do any work? If there's no work done, the change in internal energy is just Q. So the amount of thermal energy removed from the gas must have been minus 15,660. That's how it dropped. That's how the internal energy dropped. There's only one way to do it if the volume's not changing. It's with Q. So from state 2 to state 3, let's think about what's happening there. The volume of the gas is decreasing. It's going from 40 to 32. If the volume's decreasing, the piston's coming in. The piston's hitting the molecules, the atoms, not the molecules. And they're speeding up as a result. So the work done by the gas is negative. The piston's doing work on the gas. So let's calculate the work done by the gas. P delta V. Delta V is 8 liters. It goes from 40 to 32. And you have to put a negative sign in there because it's dropping. Or you just put a negative sign on the work because you know the work done by the gas is negative. So while you're trying to cool it down, the piston is giving thermal energy to the molecules, the atoms, by moving in. So the piston makes a deposit of 6230 joules of thermal energy, but the internal energy still drops by 9,350 joules. How much thermal energy did you take out? What's Q? Must be minus 15,580. 15,580 joules of thermal energy removed from the gas by cooling it. The piston made a deposit of 6,230 joules. The internal energy dropped by 9,350 joules. It should all make sense. So here's the table. State 1 to state 2, there's no work done. The volume doesn't change. State 2 to state 3, the internal energy only drops by 9,350. The work done by the gas is negative. The piston made a deposit of 6,230 joules into the system, so Q has to be minus 15,580. And these are easy to calculate. You just add up those two. And you can check that E is Q minus W for every single one of these transitions if you like to use equations. Problems involving thermodynamics can be involved in multi-step. You have to really pay attention to what's going on. A lot of times you're going to invest time taking inventory, trying to understand what the problem is asking before calculating anything. Don't be in a rush to start plugging numbers into equations. Think about what's going on. If you're relying on equations rather than understanding the concepts, you're very likely to get the wrong answer. And more importantly, if you rely on equations rather than understanding, you just aren't developing any useful skills. You're going to forget those equations, and you're not going to be transformed into a problem-solving beast. Invest in your future self by developing your brain by doing hard problems. That's the only way.